Hey guys, and welcome back to another video. In this video, we'll be talking about Newton's method. Alright, so let's get right into it. Alright, so to begin with, let's consider the graph of some function. And let's say it looks something like this. Alright, so make it look like something like that. Alright, so let's say this is y equals f of x. And so f of x has a 0 right here, right? So we'll just call this 0 to be c. Alright. So basically what Newton's method is it's like a numerical method is what we call it, like an approximation method to help us approximate the zeros of a function. So for example, if you don't know what the exact zeros of a function are, or like they're hard to like calculate by hand, you can use Newton's method, given that it meets the conditions and everything, and you can help it can help you approximate the zeros. All right. So that's why in this case, let's just say f of x is like one of those types of functions where like it's hard to compute the zeros just by like algebra or something like that. And so um we know though that f of x has a 0 at x equals c. All right. So basically how Newton's method works is first you have to pick a starting x value, right? And so to do that, you can just like test different values of x and then see like when like the function changes sign. Because like for example, let's just say like f of 1 was equal to like -4 and f of 2 was equal to 5, right? So we know that by the intermediate value theorem, um, there exists a 0 between x equals 1 and x equals 2, right? Because the function goes from below the x-axis, so like it goes from below the x-axis to above the x-axis, right? So somewhere in between, it had to have crossed the x-axis, hence it has a 0 in between 1 and 2. And so then to pick the starting x value, you would just pick the one that's closer to 0, like an absolute value. So because -4 is closer to 0 than it is to 5, I would pick x, our starting x value, which is x0, to be 1, right? And then I'll just go from there. All right. So that's just how you would start pick your starting x value. So then let's just see how Newton's method actually works though. All right. So let's just say we have some like arbitrary starting value, x naught, like right over here. All right. And so then f of x now would be over here. All right, good. So then let's go ahead and draw the tangent line to the graph at x naught. All right, so that's something like that. And so we want to see where this tangent line intersects the x-axis. So this point right here, that would be so this point right here, where it crosses the x-axis, that's our new x value. So that's going to be x1. And then you do the same thing, right? So you have you draw the tangent line to the graph of f at x1. So it looks something like that. And so now we see where this tangent line crosses the x-axis. So it crosses it right here. So then this would become our x2. And so notice that we started with x0, and then we went to x1, which is closer to our c. Then you went to x2, which is even closer to c. So in this way of like drawing the tangent lines and seeing where they intersect the x-axis, you can get closer and closer to the 0 that you want to approximate. All right, so that's basically how Newton's method works. So now let's put some math behind this concept. So we have the tangent line at x naught, right? So let's go ahead and write the equation for that. Well, we can use point slope form, all right? So point slope form. And this is a very common method to find the equation of the tangent line. We use this exact same method to find the tangent line when we use in our linearization video, all right? So it's like this exact same concept pretty much. So our point, well, we know it's just x naught, f of x naught, right? And then our slope, well, the slope of the tangent line at x naught is f prime of x naught, right? So our slope is simply just f prime of x naught. So then we can go ahead and apply point slope form. So we have y minus f of x naught equals our slope, which is f prime of x naught, times x minus x naught. Okay, let's go ahead and solve for y now. So we have y is equal to f prime of x naught times x minus x naught plus f of x naught. Okay, good. So we want to see, so this is the equation of the tangent line, okay? So we want to see where the tangent line intersects the x-axis. So in other words, we set y equal to 0, right? Because when it intersects the x-axis, y is 0. So we can go ahead and substitute in 0 for y. So we get 0 is equal to all this business, f prime of x naught times x minus x naught plus f of x naught. Okay? And so now we're trying to solve for x, because that is our, well, in this case, our x-intercept, right? That's our 0. That's our x1. So let's go ahead and solve for x. And if you do that, you should get that x is equal to x naught minus f of x naught over f prime of x naught. Okay, and so this is our x1, right? So that's how you find x1 given x naught. And so then we can generalize this to where if we're given any xn, we can find the next x, so xn plus 1. All right, and so that's basically what Newton's method is. It's just like generalizing this formula. So let's go ahead and explain what Newton's method is now. Okay, so Newton's method. All right, so basically we have some 0 of f, right? So if f of c is equal to 0, Newton's method helps us approximate c. So to approximate c, we can use the following formula. So xn plus 1 is equal to xn minus f of xn divided by f prime of xn. Okay, so a couple important things to point out is that first of all, we have f prime of xn in the denominator. So that means that f prime of xn cannot equal 0. Okay, so firstly, it's f prime of xn cannot equal 0. So like the derivative at each of our approximations cannot equal 0. And second of all, and I already mentioned this, but each iteration that you do of this, you're getting closer and closer to your 0. So xn plus 1 is approaching c. All right. So each iteration, you're getting closer to your c, your 0. All right. All right. So now let's talk about error bounds. So this is like an infinite process, right? You can just do this infinitely many times, and you're only going to get closer and closer to c, right? In some cases, you eventually will get the value of c exactly, but most of the time, it's just like you're going to get closer and closer, but you're never actually going to get the exact value of c, right? And so then, because it's infinite, obviously we can't do this infinitely many times. So therefore, to turn this infinite process into a finite process, we have a thing called an error bound, right? So the concept of an error bound, and it's usually denoted by epsilon. So error bounds are basically like, let's just say I give you like some epsilon, right? So like usually epsilons are pretty small. So let's just say we have epsilon is equal to 0.001, right? So what an error bound is it says that, okay, if two consecutive values of xn, so like if xn and xn plus 1 differ by less than epsilon, so by less than 0.001 in this case, then you can stop, right? That's good enough for our purposes. So that's why error bounds are very good. It helps transform this infinite process into a finite one, right? All right, good. So now that we have that out the way, we can move on to some examples. Okay, so this is our first example. So we have to approximate the 0 of this function using Newton's method, all right? So we have f of x equals 2x cubed plus x squared minus x plus 1, and we're given an error bound epsilon of 0.0001, okay? So basically all this means is that once we get two consecutive x values whose difference differs by less than this, then we can stop, right? All right, good. So like I said, to begin with, in Newton's method, you need like a starting point. So how do you find it? Well, you could just like test different values of x and then see when they change signs, right? So let's just test values of x, right? So if we have like f of -1, let's just say, right? So that's 2 times -1 cubed plus -1 squared minus -1 plus 1. So this is equal to a 1, all right? And so now that's positive, right? So this is 1 greater than 0. So if we test like some other value, let's say f of -2. So if this is negative, then that means that we know the 0 lies between -1 and -2. And so then we can just pick whichever one is closer to 0 and then use that as our starting x value. So -2, if we find that, we have 2 times -2 cubed plus -2 squared minus -2 plus 1. And this should give you a -9. Okay, so that is less than 0. So that means that our 0, by the intermediate value theorem, it has to lie somewhere in between -1 and -2. So now, which one do we pick, -2 or -1? Well, 1 is closer to 0. It's closer to the x-axis than -9, right? So therefore, I want to pick our starting value x0 to be 1, or sorry, -1, because then we will approach the 0 quicker, all right? So therefore, I'm going to let our starting value x0 to be -1. All right, good. So now let's recall Newton method's formula. So it's xn plus 1 equals, I'll write it over here actually. So we have xn plus 1 equals xn minus f of xn over f prime of xn. Okay, so that's our formula. So in order to find x1, that's equal to x0, so -1, minus f of x0, so f of -1 all over f prime of -1, right? So let's go ahead and evaluate this. So we have -1 minus f of -1. We already evaluated that up here. It's 1. And then over f prime of -1. So we need to find the derivative of f. So let's go ahead and compute the derivative. So we have f prime of x is equal to, so we have 6x squared plus 2x minus 1, right? Just by the power rule. And so if we find f prime of -1, that is equal to 6 times -1 squared plus 2 times -1 minus 1. So that gives you a value of 3. All right, so f prime of -1 is 3. So therefore, x1 is equal to -1 minus 1/3, which is -4/3. And we can write this as a decimal as well. So it's approximately -1.3333. All right, good. So let's stop and check real quickly. So -1 and -4/3, the difference between them, the absolute value difference, is a third. It's like 0.33 repeating. But so is that less than our epsilon though? It isn't, so that means we have to keep going. All right, so after you compute each x value, just like quickly stop and check and make sure that, or see if like you're less than your epsilon, because then you can stop, right? Prevents you from like doing extra work. All right, so x2 is equal to, so we have x1, which is -4/3, minus f of -4/3 all over f prime of -4/3, right? So you can go ahead and put this into your calculator real quickly. Okay, and you should get a value of approximately -1.2434, right? So again, let's stop and check. The absolute value difference between this and this, is that less than our epsilon? No, it isn't. So that means we have to keep on going, all right? So x3, that's equal to x2, so -1.2434 minus f of -1.2434 all over f prime of -1.2434. And I would like to stop real quickly and mention that when you're like showing your work and stuff, it's okay to write the rounded off version of like the number, but when you put it into your calculator, just make sure that you're putting like the actual fully unrounded decimal expansion, right? Because that just makes the approximations more accurate, and also it helps you do less work because then like there's like less rounding error, right? So go ahead and you can pause the video now and make sure to put like the full decimal rather than just the rounded version, right? All right, good. So hopefully you got a chance to put in your calculator. So you should have gotten approximately let's see, -1.2339. All right, so we're getting closer. Okay, our difference between this is like only like 0.01, something like that, and we want 0.0001. So it's still greater, but we are making progress, so that's good. All right, let's go ahead and compute x4. So x4 is equal to x3, so negative 1.2339 minus f of x3, so f of negative 1.2339 divided by f prime of negative 1.2339. So again, go ahead, pause the video, put this into your calculator, put the full decimal, and let's see what you get. All right, cool. So you should have got in approximately negative 1.2338. So if you compute the absolute value difference between these two numbers, you actually get exactly 0.0001. So now this just comes down to like a matter of preference. Some professors may accept it if it like the difference is equal to epsilon. Some may require the difference to be strictly less than epsilon. Although like if you compute x5, you're definitely going to be less than epsilon, so that's like the safe play is just like compute one more if it's equal to each other, and then like, you're definitely within that range. But just for like the sake of time, I'm just going to say that this is a pretty good approximation for our zero. All right, so x equals negative 1.2338 is a very good approximation for the zero of our function f of x. All right, let's move on to another example. Okay, so this is our next example. We have f of x equals x minus 2 square root of x plus 1, and our error tolerance this time is 0.001. Okay, so again, we need to find a starting point. So let's go ahead and just, test some values of x. So we could just like start with 1. So f of 1 is equal to 1 minus 2 square root of 1 plus 1. So that's like 1 minus 2 root 2. So that's a negative value. Okay, so this is like some negative value. So then now we could like test f of 2, right? So let's see, we have 2 minus 2 root 2 plus 1. So we have 2 minus 2 square root of 3. That's still negative. Okay, so I have a feeling this is going to be negative for quite a while. So let's like make a jump to like x equals 5, let's just say. So if we test f of 5, we get 5 minus 2 root 5 plus 1. So that's 5 minus 2 square root of 6. All right, so this is 5 minus 2 root 6. So root 6 is like right above root 4, right? So it's just over 2. And so therefore, 2 root 6 is right over 4, okay? So we have 5 minus something just above 4. So this is going to be positive, but it's also going to be very close to 0, right? So we have some positive number that's also very close to 0, though, because we have 5 minus 4 point something, okay? So, yeah. But okay, so f of 2 is negative, f of 5 is positive, so our 0 must lie somewhere in between. And just because f of 5 gave us a value that's closer to 0 than f of 2 was, we're going to use our starting value to be x equals 5. All right, so let's go ahead and set our starting value x naught to be 5. Right, so as you saw in the previous example, we need the derivative of f. So let's go ahead and compute the derivative of f now. So we have f prime is equal to 1 minus 1 over square root x plus 1. And again, this is just a simple application of the power rule. Okay, very good. So now let's go ahead and find x1 using our formula. So we have x1 is equal to x naught, which is 5, minus f of 5 over f prime of 5. All right. And so if you were to put this into your calculator, you get a value of approximately 4.8293. So the difference between 5 and 4.8293 is definitely greater than our epsilon. So you must keep going. So x2, that's equal to our x1 value, so 4.8293 minus f of that over f prime of x1. And again, go ahead, put this into your calculator, put the full decimal version, like always, and you should get a value of approximately 4.8284, right? All right, good. So it seems that our difference is less than 0.001 now. Let me just check real quickly. Yeah, because we have 8, 4, and then 9, 3. So that is less than 1. So I think we could just stop here, right? So that's pretty easy. So like, as you can see, some of them may require like 4 or 5 iterations, while some only require like 1 or 2, right? So it just really depends on like your problem, and more importantly, your starting x value. So in this case, x naught equals 5 was probably a better starting point than I think it was like x naught was equal to -1 in the previous case. Yeah, so it just really depends on your starting value. So we can confidently say that our 0 of this function is pretty close to 4.8284. All right, nice. All right, let's move on to our final example now. All right, so this is our final example. We have f of x equals cube root of x, right? So I know what you're probably thinking. You're like, isn't the 0 of this quite obvious? It's just 0, right? And yes, you are correct. F of 0 does indeed equal 0. So therefore, x equals 0 is a 0 of f of x. And in fact, it's the only 0 of f of x. So then why would I include this problem in Newton's method if like you could just solve it algebraically? Because Newton's method actually fails for this problem. So algebraically, we know that the solution is x equals 0, but Newton's method actually fails. And let's see why that is. Well, it's because f prime of 0 is undefined, right? So if we find f prime of x, it's 1/3 x to the negative 2/3 power, right? And so if you find f prime of 0, we have 1/3 times 0 to the negative 2/3. So that negative in the exponent means that 0 is in the denominator. And so then you're dividing by 0, so therefore f prime of x, or f prime of 0, is undefined. Okay? And so then it should be evident why that's a problem, because in our formula we have xn plus 1 equals xn minus f of xn over f prime of xn. And so if our solution, if our 0 is x equals 0, that means that our xn's, our x values are getting closer and closer to 0. So each time we evaluate f prime of xn, we're getting closer and closer to evaluating f prime of 0. And so therefore, but f prime of 0 is undefined, so therefore Newton's method just completely breaks in this case, right? And then like geometrically, like if you want to look at it graphically, the reason why this fails is because we have the, okay, so let's just sketch the graph of cube root of x real quickly. So we have, it will look something like this, right? So we have, roughly speaking, it looks something like this, okay? And so we know, so this is cube root of x. And so we know that we have a 0 right here, right? So let's just pick any arbitrary starting point. So let's just say I pick x naught, my starting point, to be right here. So we draw the tangent line to this graph at that point. So we end up right here. Notice how we actually got farther away from the 0 than x0, right? x1 is farther from 0 than x0 is. But okay, maybe it was just a coincidence, right? Maybe we'll get closer eventually. So let's go ahead and draw the tangent line at this point. So we have something that looks like that. So now x2 is over here. So it got even farther than x1 was. And this pattern just keeps continuing, right? Every single time you draw a tangent line, the place, like the x value where the tangent line intersects the x-axis, keeps getting farther away from 0. So therefore, it doesn't even converge to any value. The Newton's method actually diverges in this case, right? It just blows up to infinity. And like to see that algebraically, we can like compute xn plus 1 by substituting in the actual formulas. So what I mean by that is like we can compute xn plus 1. So xn plus 1 is equal to xn. And then f of xn is simply just the cube root of xn, right? So just the cube root of xn all over f prime of xn is just, let's see, this right here, right? So 1/3 times xn to the negative 2/3. So I'm going to go ahead and rewrite xn, or cube root of xn, as xn to the 1/3, right? It's the same thing. And so then this simplifies to xn plus 1 equals xn minus 3xn. Okay, and so then we get xn plus 1 equals negative 2xn. So this is actually very like interesting, because we have xn plus 1 equals negative 2xn. So for each value of xn you get, you're multiplying it by negative 2. In magnitude, that's just getting bigger and bigger, right? So as as you increase your values of xn, like as you keep iterating through, our xn's are just diverging off to infinity or negative infinity. It actually doesn't converge at all. So that's like a graphical reason why Newton's method just completely fails in this example, right? So that's just your heads up that Newton's method works, but not always, right? So in this case, it's just because the tangent lines are diverging. But yeah, so that pretty much wraps up this video on Newton's method. If you found this video helpful, please make sure to leave a like and don't forget to subscribe. I'll see you guys in the next video.